welcome to 27th Theoretical Physics Colloquium at ASU. I'm very glad to present Professor Steffen Boss, who is Arts and Science Distinguished Professor of Physics at Duke University. He got his PhD in 1997 from Goethe University in Frankfurt. He had 2 postdoc positions. One of them was Further-Linen Fellow and Research Associate position at Duke University between 1998 and 99. He then was visiting assistant professor at Michigan State University in between 99 and 2000. He got a faculty position at Duke University in 2000. For the first 5 years, he was also RHIC and Biennale Research Center Fellow. He stayed at Duke University since then. Between 2015 and 2019, he was an associate department chair at the Department of Physics of Duke University, and since last year, he is a department chair. He received several honors while at Duke. He was an outstanding junior investigator from the US Department of Energy. He received an award of outstanding referee from the American Physical Society, and he became the fellow of the American Physical Society in 2015. He served as the member of several editorial boards of several journals, PRC and Journal of Physics, and he did a lot of other professional service to the community, and I'm very glad that he agreed to give a talk today about the shear viscosity in Quark-Gluon Plasma. So please, you may start.
Thank you, Igor, for the kind introduction. Wow, I'm glad that I actually get the time to do some physics today. And I'm going to tell you a story about a data-driven approach to quantifying the shear viscosity of the Quark-Gluon Plasma. And since this is a colloquium, I'm going to start out fairly basic. If you look at the building blocks of matter, yes, this could be living matter like a fly, or non-living matter like the desk I'm sitting at. It's made up out of molecules, which in turn are made out of atoms that have an atomic nucleus inside. The atomic nucleus is in turn made up out of protons and neutrons, and these are made up out of quarks and gluons. Yes. Where we often associate sort of the matter part really with the quarks, if we consider the gluon being the gauge boson that mediates interactions among the quarks. All right, so matter has, according to the standard model of particle physics, has 12 building blocks, but we really only need 3 for the creation of ordinary matter, like our fly or our table, right? We need up quarks, down quarks, and the electron. The force I'm going to be talking about today is the strong force, one of the 4 basic forces of nature, that mediates interactions between protons and neutrons or between quarks via the exchange of gluons. And this is governed by a quantum field theory called quantum chromodynamics. Okay, now particle physics deals with the study of elementary interactions and probing these to see whether there are any interactions beyond the standard model. Nuclear physics, for the most part, actually deals with many-body systems. Yes, and so I'm going to go to a really many-body system. Yes, and I'm going to start out again with ordinary matter. Let's take water as an example. And water at room temperature is a liquid. Yes, if we freeze water down to below 0 degrees, or if we cool water down to below 0 degrees, it turns to solid. And if we heat it up to above 100 degrees Celsius, it turns gaseous. Yes. However, temperature is not the only control parameter that we have. Yes, if I would do my experiment about the different states water can be in on Mount Everest instead of on sea level, then I would find that the transition between liquid and gas happens actually at 71 degrees Celsius. Yes, so the state water is in depends both on temperature and on pressure. And mathematically, we refer to this connection between temperature and pressure and the state particular matter is in as the equation of state. Okay, So for ordinary matter like water, this is a concept we've grown up with, that we've known for hundreds of years. Let's turn now our attention to other forms of matter like QCD matter. So one thing I should add for ordinary matter is that if I want to understand theoretically how these phases come from and at what temperature and at what pressure I have what kind of phase, solid, liquid, or gases, yes, then I can, from the theoretical side, I can figure that out if I know the interactions between the molecules, yes. So the phases are determined by the interactions between the molecules. In the case of water, it's actually the van der Waals interaction between the water molecules, yes. And on the theory side, if I can calculate the partition function of that particular system, yes, I can take the derivatives of the partition function, and that gives me the equation of state. And as you can see here, the equation of state for water can be complicated. So it's not only liquid and a solid and a gas. You can have a supercritical fluid. You can have a triple point, a critical point. Yes, where all these phases meet. So every substance has its own phase diagram that can be pretty rich in terms of the structures that you observe. All right. So what about the phase diagram of QCD matter? And one of the reasons you can ask this question is that an atomic nucleus behaves very much like a liquid drop. Yes, that was one of the profound discoveries, I guess, in the 1930s. And you can argue now, if the atomic nucleus behaves like a liquid drop, at what pressure or at what temperature can I get it to boil? At what temperature or pressure can I get it to go into a gaseous phase? Can I cool it down to a solid? Yes, so these are all legitimate questions, and you can summarize them in asking question, what is the phase diagram of nuclear matter? Yes. So if you want to do that, you need to find a way how to heat and compress nuclear matter or QCD matter. And really the only way to do that is by colliding heavy atomic nuclei. And I'll talk about that a little bit later in my colloquium. On the theory side, again, you will need to solve the partition function. And that is being done via lattice field theory and requires a very, very significant computational effort. So in the background, you can see an IBM Blue Gene computer, which I believe once sat at Brookhaven National Lab, and was one of the first computers to really do a serious job in evaluating the QCD partition function and calculating the equation of state of QCD matter. And one of the early results of these calculations can be seen here in this plot. So what's plotted is, as a function of temperature, the energy density divided by temperature to the fourth. And this is a lattice field theory calculation for QCD matter. And I'm not going to go into the details of the calculation. What you should take away from this figure is that in this representation, you see something like a step function. So why is this interesting? Well, you can make an approximation. Yes, the approximation would be that my QCD matter is at a high temperature, and so I'm going to approximate it as a system just of gluons. Gluons are ultrarelativistic massless bosons, and you can consult the statistical mechanics textbook for the equation of state of a gas of ultrarelativistic massless bosons, and it takes on a very simple form. It takes on the form that energy density equals some numerical prefactor times the degrees of freedom of the system times temperature to the fourth. So bringing T to the 4 over to the left-hand side means that my right-hand side basically just becomes a measure of the number of my degrees of freedom. And when I see a step function here, this means I have a rapid change in my degrees of freedom. So this is indicative of a phase transition if it were a clear step, or a phase change if this is somewhat of a gradual change. And what these lattice field theory calculations have told us is that there is, a phase change, a transition in QCD matter from one form to another. And, it's reasonable to assume that it's, from the confined form where you have, quarks and gluons bound in protons and neutrons, to a deconfined form, a plasma phase, where quarks and gluons roam freely. And we learned that the temperature at which this happens is around 200 MeV. Yes, if you look at the latest lattice field theory calculations, including quarks, yes, that temperature is now in the vicinity of 155 to 160 MeV. All right, so we know that QCD has a phase change. It's something interesting for us to study. Yes. In the middle figure, you have sort of a cartoon for a QCD phase diagram. In this case, it's plotted temperature versus biochemical potential, which is a measure of quark density. Yes, and there is the expectation that this phase diagram has a critical point. On the right-hand side of the critical point, you would have a first-order phase transition, and on the left side of that critical point, you would have a crossover. The precise location of this critical point, or even its real existence, hasn't been fully established yet. So it's been conjectured by virtue of lattice field theory calculations along the temperature axis at zero biochemical potential, giving us a crossover transition, and other means of calculating the phase diagram for zero temperature along the biochemical potential axis, giving us a first order phase transition. And so at some point this has to shift from one to the other. Could shift multiple times though, so we don't know that. Okay, so another reason why the study of QCD matter is interesting is cosmology broadly, in a broad sense, right? So we know from celestial observations that the universe and all the matter in the universe originated from one point in space-time that we refer to as the Big Bang. And so as the universe expanded at some point early on in its lifetime, a few microseconds after the Big Bang, it was still so hot and so dense that it was above the temperature for the transition to deconfined quark and gluon matter. So at that point, the entire universe was in a Quark-Gluon Plasma stage. And if we now investigate the properties of this Quark-Gluon Plasma, then we do not only learn something about the properties of QCD matter, but we also learn something about the properties of the early universe. Okay, and the only way we can do this experimentally really is by colliding two heavy atomic nuclei. And I shall again go to that a little bit later. Before I go there, I want to introduce another concept, namely that of viscosity, or more generally speaking, transport coefficients. So for my purposes, the shear and the bulk viscosity of a system that I can characterize by a stress energy tensor are defined as the coefficients in the expansion of that stress energy tensor in terms of the velocity fields. So the shear viscosity sits here and the bulk viscosity sits here. Yes, and so those transport coefficients are standard properties of every form of matter. Now one could ask the question, since I'm able to evaluate the equation of state of QCD matter using lattice field theory, can I do the same thing for the transport coefficients? And the answer is that this is a much harder problem to do on the lattice. Yes, that's due to some formal reasons. You have to take a zero momentum limit in an infinite spatial volume, and that is not very well defined. There have been brave souls who have tried to use some tricks in order to make some estimates on the specific shear viscosity at various temperatures, and they are listed here. But you can see that the uncertainties in these determinations are of order 1. Yes, so there's 100% uncertainty in it. And so the question is whether there are other ways how we can access these properties of QCD matter, the viscosities, instead of relying on these very, very difficult lattice field theory calculations. And so it turns out that the determination of these QCD transport coefficients has become one of the key goals in the global relativistic heavy ion effort. And that has to do a lot with the success of fluid dynamics for the modeling of these heavy ion collisions. Okay, so success of fluid dynamics. Early on, after the relativistic heavy-ion collider turned on, it was found that fluid dynamics is a very good way of describing the outcome of these heavy ion collisions. Yes, as a matter of fact, initially, ideal fluid dynamics, which does not contain any viscosities, seemed to work rather well. And somewhat later on, it was argued, and I think it makes perfect sense, that ideal fluid dynamics is too big of an approximation. Every system in nature, has a viscosity, and only in the limit of zero mean free path would you get away from would you have zero viscosity, and clearly, a system like the Quark-Gluon Plasma does not have zero mean free path. So Chernai, Kapusta, and McLaren wrote a seminal paper where they were speculating on the specific shear viscosity, the ratio of shear viscosity over entropy density of the Quark-Gluon Plasma, and how its temperature dependence would be. Yes, this was also motivated by a discovery out of string theory that conjectured a lower bound for field theories that were similar to QCD for this quantity to be 1/4 pi. And so Kapusta, Chernai, and McLaren took a more phenomenological approach. They looked at helium and water, looked at the specific shear viscosity for those substances, and plotted what was known at that point for the specific shear viscosity of QCD matter. And really, this is a log scale here. The range of temperatures that is accessible in heavy ion collisions was sort of the big unknown. You could do calculation of a pion gas that had this very quickly rising eta over S, and you could do calculations of a very, very hot, perturbative, weakly interacting QGP that had a logarithmic rise in temperature here. But that calculation sort of breaks down somewhere around a few hundred MeV temperature. Yes, and but basically what these authors stated is that, all right, this is what we know, and it is reasonable to assume that there should be probably a minimum in eta over S at the phase transition, as we've seen from helium and water, and that it could very well be in the vicinity of 1/4 pi, yes, which is down here, and which is the string theory conjecture. All right, fast forward 12, 13 years. Here's the punchline of my talk. This is the modern version of the figure you see on the left-hand side, yes, with water, helium, and now a curve for the temperature dependence of the specific shear viscosity of the Quark-Gluon Plasma extracted from a model data comparison via Bayesian analysis. Yes, and it really fills exactly in this gap. It goes from about 150 MeV right here to 250, 300 MeV. So it's in this range, and you can see, okay, this is a log scale. Yes, so we are starting at the low point at about 0.1. Yes, which is very, very close to the 1/4 pi value from string theory, actually. And this is an extraction from experimental data, yes, using viscous fluid dynamics. So for the rest of this presentation, I'm going to tell you how we actually did this calculation. All right, so first let's take a brief look at the experiments, at the data that we need for our analysis. Yes, and those are generated by heavy ion collider facilities, in particular for this analysis from the Large Hadron Collider. Yes, and these colliders are really the only way to heat and compress QCD matter under controlled lab conditions. Yes, and the LHC has several experiments. For us, the most relevant experiment is ALICE, which is sort of custom built for the study of the collision of heavy nuclei and for the study of the Quark-Gluon Plasma. This is the ALICE detector. It is being operated by over 1,000 scientists from over 100 institutions worldwide. It is a massive device. It weighs 10,000 tons. And believe it or not, this device is quite a bit smaller than the other two major detectors at CERN, CMS and ATLAS, which played a pivotal role in the discovery of the Higgs boson. Yes. So what do these detectors see or measure? What is the data? Yes. So a typical particle physics event. Yes. This one by the ATLAS, measured by the ATLAS detector, is for a proton-proton collision where you produce about 30, perhaps 40 maximum. Okay, you can go up to 200, but on average, you're producing a final state that has 10, 20, 30 particles. And you can see here these tracks. These are all tracks measured by the ATLAS detector. Each track stands for a particle, and these bars are sort of the energy that these particles deposit in the calorimeters that are part of the detector. And you can see that this is, I would argue, a somewhat dilute environment, so it is fairly straightforward to analyze this and characterize each of these tracks. Which particle was it? Is it an electron? Is it a proton, a pion, a kaon? And thus come to a complete characterization of the final state. All right, now this is not what ALICE measures when you have a lead-on-lead collision. This is what ALICE measures when you have a lead-on-lead collision. So you have thousands of particle tracks, and the real challenge is to reconstruct the final state and to characterize the matter created in this collision from these thousands of tracks. Yes. So this detector clearly is optimized to record a lot of tracks, and then with reasonable accuracy, characterize the event by identifying the particle that each track generates. Yes, but hey, if a handful of tracks are misidentified, it's not that big of a deal because you're dealing with a collective. Yes, which would be fatal for any Higgs search in ATLAS, yes, where you really need high precision to characterize every single track, because otherwise you don't understand your final state. Okay, so how do we, from a theory side, approach this type of data? Yes, this is a dynamical environment. Yes, so we can't do it with lattice field theory, which operates in the infinite time, infinite volume, fixed temperature limit. Yes, a heavy ion collision is at finite time, finite volume, rapidly changing temperature, right? So it's everything that a lattice field theory calculation is not. So you need a different type of theory. Yes, so transport theory is what we use, and transport theory can take many different forms. Yes, you can construct a microscopic transport theory, microscopic meaning that you're really looking at individual quarks and gluons or individual protons and neutrons. So you're treating every particle as a degree of freedom. Yes, and the Boltzmann equation describes basically the time evolution of a system of microscopic particles that interact through scattering, binary scattering. Yes, the polar opposite of that, even though you can derive one from the other, is fluid dynamics that makes the assumption that I have so many particles in my system that it would be totally impossible to treat every one of these particles individually. So I basically coarse grain my system into fluid cells that have a well-defined energy and a flow velocity. And then I just solve basically the fluid dynamical equations in order to describe the energy and momentum flow of the system. Yes. There are other forms of transport theories. I could make an approximation where I say I'm just interested in some special particles that undergo a diffusion process in a thermal background. That could then be modeled with a Langevin equation. Or I could actually develop a hybrid model that sort of takes the best of two worlds, right? It takes the best of the fluid dynamic world and the best of the microscopic transport world and combines them to come up with a better, more realistic transport description. And that's what we are going to do in our case. Yes. No matter what transport theory you choose to construct, yes, each of these models that you build relies on parameters that describe, the time evolution from the collision, from the initial state to the final state. Yes, and these parameters are a representation of the information that you can extract. Yes, so by tuning these parameters, you learn something. Yes, these parameters have to stand for certain physics processes or physics properties. for example, in fluid dynamics, yes, the parameters you would need are, since this is a set of partial differential equations, you would need an initial condition that is governed by a set of parameters, and you would need, for example, the transport coefficients that would be governed by a set of parameters, and you would need an equation of state. This is the connection between energy density and pressure that in our case would be given by the outcome of a lattice field theory calculation. Okay, so how does a microscopic calculation or actually a hybrid transport model do a heavy ion collision? So here's a visualization of such a calculation. We start out with two colliding lead nuclei, which are Lorentz contracted since they're approaching close to the speed of light. As they collide, a quark-Gluon plasma is formed, which is modeled in fluid dynamics. It expands. At that point, it cools down. Those are the colors in the contour lines. Here is a missing contour line, at which point we are at a temperature where it makes more sense to convert the system into an ensemble of particles and evolve these particles then using a Boltzmann equation. Yeah, so this is a hybrid approach where we model the hot and dense phase of the reaction with fluid dynamics, and the later dilute stages of the reaction, when the mean free paths of the particles get large, we model with a Boltzmann equation. Okay, this is a visualization of an actual calculation. The actual calculation takes about 1 hour on a CPU for one such collision event. All right, so if we want to probe, how do we now probe the QGP in heavy ion collisions? We have our dynamic evolution that is being modeled with a transport model. What the experiments actually measure is the final state, the particles that come out of this stage here when they have ceased interacting with each other. What we are interested in are the properties of the system up front here. Yes, this is where our Quark-Gluon plasma lives. Yes, so we basically we are using our transport theory to make the connection between what can be measured back here to what's interesting in the intermediate stages here. And again, we start out with nuclei colliding at nearly the speed of light. The Quark-Gluon plasma gets formed. The Quark-Gluon plasma decays as it cools into a state of hadrons that we scatter and then end up as tracks in the detector. Okay, now in terms of mathematical modeling, the early reaction phase is out of equilibrium. Prior to a Quark-Gluon plasma forming, there is no equilibrium whatsoever in the system. So you need some kind of non-equilibrium early time dynamics calculation to model that. Then once a Quark-Gluon plasma has been formed, you can feed that into a fluid dynamical calculation that runs all the way until you decide using some criterion, in our case, a temperature threshold, that we are going to convert the system into an ensemble of particles, hadrons, and evolve them through a Boltzmann equation to the very end. All right, so what are the principal challenges of probing a QGP with heavy ion collisions? Yes, the time scale of the collision process is 10 to the negative 24 seconds. So you cannot see that, or you cannot resolve that in your experiment, in your detector. You only get to see the ashes of the decay of the Quark-Gluon plasma. The length scale is 10 to the negative 15 meters. Again, this is not something you can resolve, right? So what you measure essentially is momentum space information, but not really a lot of position space information. And then there is confinement, one of these pesky properties of quantum chromodynamics that states that you cannot observe an individual quark or gluon roaming freely in nature. You can only observe color-neutral bound states of quarks and gluons in nature. Yes, and so it's really these computational models that are needed to connect what you observe in the experiment with what you want to investigate here and here.
Sorry, can I ask you a question?
Just yeah, we have two questions. Go ahead.
Could you please explain a little bit more why the Boltzmann distribution method fails from the beginning? I mean, I could put a more complicated collision integral from the beginning, right? Why do I need to use this hydrodynamic stage in the beginning?
Okay. Well, yes, you could start out with for example, some kind of color Vlasov-Wheeling-Uhlenbeck equation up front. That is hard to do, yes, given the approximations you would have to do, since you could not use PQ perturbative QCD. So the coupling constant gets large in QCD, and that means that for these microscopic transport approaches for which you require cross sections or reaction rates, you need to find a way how to calculate those. And if you cannot use perturbative methods, this becomes very, very hard. Yes, the big advantage of fluid dynamics is that it hides those details that you don't know how to rigorously calculate. Yes, and in particular, it's all in the equation of state, and the equation of state you can get from lattice field theory with a reasonably good precision. Yeah, so we really know how to calculate in the mu b equals 0 limit the equation of state of QCD matter. Yes, and that is the main input apart from the viscosities in the fluid dynamical calculation. So it's a pragmatic choice. Yes, in the absence of our knowledge of all the intricacies of the microscopic dynamics of a system of deconfined quarks and gluons.
Thank you.
Okay, the other question is about the going from viscous hydra to hadronic transport. Is it all happening for the whole system at once, or is it going gradually from the edges to the inside?
It goes gradually. So what we do is it's so-called a local criterion. As soon as a fluid cell reaches a threshold temperature, yes, we convert that fluid cell into an ensemble of particles. Yes, so this means that this conversion process is something that happens over a fairly long time scale, and yeah, roughly speaking, from the outside in. Yes, and the temperature at which we make this transition becomes actually a parameter of our analysis. Yes, so we don't assume what that temperature is, but our analysis will tell us what that temperature is at which we should do that. Does that answer the question?
I think so. Yeah, thanks.
I mean, you can ask me in the discussion time later. There are computational tricks that we have to do in order to make this work. But that's the basic idea. Okay. So knowledge extraction. So how have heavy ion physicists over the last decades actually gone about learning something from these complicated systems? So you take the data that the detectors deliver, particle tracks, you convert those into particles with a momentum and a particle ID, which gives you sort of its mass and its charge. And then you do data reduction, right? You calculate histograms for momentum distributions or angular emission distributions, all sorts of histograms, and those you plot, and you have now a computational model where you do a similar data reduction, where you basically calculate the same kind of quantities, and then you compare the two. And if you find an agreement, yes, then you assume your model to be correct, and you interrogate your model about what kind of physics it contained to give you this agreement between the model histograms and the experimentally measured histograms. Yes, that worked reasonably well as long as our models were simple and our data was sparse. It does not work so well anymore if you generate petabytes of data, which gives you hundreds of histograms of different observables, and if you require a model that does a reasonable job in describing all of these data and not just one particular distribution. Okay, and here, so to speak, a visualization of this challenge, right? A good model that can describe a lot of features that are seen in the experiment can have more than a dozen parameters, from the equation of state to the viscosities, initial state, and so forth. On the experimental side, you measure a lot of stuff. You measure multiplicities and distributions for the momenta of particles. You measure them as a function of centrality, which is a stand-in for impact parameter. You measure collective motion of particles. You do particle interferometry. You do correlations of charges. You do correlations of particle momenta. Yes, and it turns out that my model parameters can affect, multiple. Each of my model parameters can affect multiple of these experimental observables. Yes, so in the end, you have this fairly chaotic interconnectivity where every one of my parameters affects every single piece of data that I measure. Yes, and this means, so I don't have a factorized problem where I could say, all right, my shear viscosity is only governed by the flow. So I can tune my shear viscosity by just looking at the flow observable. And my whatever equation of state only governs my momentum distribution. So I can tune that through that. I cannot do that. Each of these parameters will affect every single observable. So I have a large number of interconnected parameters with non-factorizable data dependencies. My data have correlated uncertainties that come from the way the experiment is set up. Yes, and so I need to develop novel optimization techniques, for example, coming from Bayesian statistics, in order to do a simultaneous optimization of all of my parameters to all of the data at once. Yes, and then the next challenge is that requires, of course, doing a lot of calculations to explore the parameter response of my theory, and that could kill me as well. Now, fortunately, this is a general problem. It's not restricted to QCD or nuclear physics. It's something that you have in cosmology and the atmospheric sciences. You have that in many areas of the hard sciences. And so our friends in statistics have developed very powerful tools that help us address this kind of challenge. And for the rest of my presentation, I'm going to talk about these tools. Okay. So I've already stated that each computational model relies on a set of physics parameters that describes the dynamics and the properties of the system. Yes, these parameters are a representation of the information I wish to extract. In the olden days, I would guess, what parameters are relevant. I would run my model with those parameters. I would then calculate observables and compare to data. And if that comparison pans out well, then I would say, fine, I found my parameters, I found the values of my parameters, I'm done. Yes, and otherwise I would iterate. Yes, and that is a cumbersome process. In a Bayesian analysis, I'm sort of turning this arrow backwards, right? I take all of the data and interrogate the model, what it takes in terms of parameter values to describe all of these data in the best possible way. Yes. And I even do so, and in this process, I even get out the uncertainties that come with my parameters, right? No physics parameter that I put in my theory is known with ultimate precision. It always comes with an uncertainty, and and we need to treat that seriously. Yes. Okay. So one example where this type of Bayesian analysis has been very, very successful has been in the discovery of gravitational waves. Yes, LIGO, the gravitational wave observatories, they measured a signal, yes, which you can see here. Yes, it's a fairly noisy signal. And what they had to do was a model to data comparison. They had to compare the signal with a model for the merger of two black holes or two, massive objects that gives the same kind of signal as output as what the gravitational observatory measures. And by tuning the model parameters to the signal, yes, that's how they were able then to make this discovery and come up with these probability distributions for the masses of the two celestial objects that merged. Yes, so that is a poster child for Bayesian analysis. Okay, so here is a scheme for the analysis that I'm going to conduct, and for the rest of my talk, I'm going to walk you through each one of these boxes, so you get an understanding on what it takes to do such an analysis and to get at a quantity like the specific shear viscosity. And you will learn hopefully something new in the process. For example, this little trick, which is called the Gaussian process emulator, which really saved us from total failure. All right, so let's take a look at the components, and I'll start out with the physics model. And we've already talked a little bit about fluid dynamics and Boltzmann equations. So I'll be brief here. I could give a whole talk about just how to build these kind of models, but that's not what today is all about. So in order to simplify our life, we are not going to create a model that dynamically treats the early pre-equilibrium phase of the heavy-ion collision. We are going to use a phenomenological model that basically drops in an initial Quark-Gluon Plasma configuration and does it in a way that is very adaptable to a variety of physics scenarios that could lead to this configuration. And that phenomenological model is called Trento. Once we have an initial Quark-Gluon Plasma configuration, we are going to evolve it through a 2+1D viscous fluid dynamical calculation. The equation of state will come from lattice field theory, and my main parameters in this stage of the simulation are temperature-dependent shear and bulk viscosities. Then I have a parameter that determines at what time I switch from fluid dynamics to a Boltzmann evolution. And after that, I use a microscopic transport model based on the Boltzmann equation, Euro QMD, for the breakup of the system up to the point where I get measurable particles out of it. Yes, and Euro QMD has the big advantage that it's been around for 20 years and has been already calibrated on a lot of lower energy data. Yes, so I can use this without having to worry too much about not knowing what the hadronic physics is. That's fairly well understood. And also another advantage is, since it's a microscopic approach, the physics of shear and bulk viscosity are already implicitly contained in the calculation. Yes, so I don't have to worry about calculating the shear and bulk viscosity in the hadronic phase. It's implicit in the model, and I can thus focus on the shear and bulk viscosity of the Quark-Gluon Plasma, which is what I'm really interested in. Okay, what are my parameters? I've already mentioned some of those. Yes, I have the temperature at which I'm going to switch from fluid dynamics to microscopic evolution. That is one of my parameters. I have the parameters for my initial Quark-Gluon Plasma configuration. These parameters don't have an a priori physical meaning, but we can relate these parameters to certain physical properties of the system. Yes, of particular interest will be this parameter P that distinguishes between different classes of initial state models that are out there in heavy ion physics. And for the experts, this would be the distinction between a wounded nucleon model, a KLN type scaling model, and an IP Glasma type model, which were sort of three major initial conditions that we were playing around with when we were doing this kind of physics. Okay, then we have a simple polynomial ansatz for the temperature-dependent shear viscosity, and a simple polynomial ansatz for the temperature-dependent bulk viscosity. Yes, yes, okay. All right, so the data we take are from the Alice experiment, and it's mostly momentum distributions and flow distributions. And I'll talk a little bit more about flow right here. Yes, so if you collide two nuclei at relativistic velocities, or at any velocities, as a matter of fact, you will rarely collide them directly head on. You can't aim these particle beams. It's physically impossible to aim them directly and to control the impact parameter. So most times you will get a partial overlap between your colliding nuclei, and that means that the zone of matter that you heat up and compress has this almond shape. Okay, this almond shape is hot, it's highly compressed, it wants to expand. So it's going to expand in a collective way. It's going to expand predominantly in the reaction plane, because the expansion will go normal to the surface. Yes, and so you will have a lot of it will be preferentially expanding along this axis and not so much along this axis. Yes, and this type of buildup of flow, yes, where you convert a position space configuration of compressed matter into a momentum space response, yes, is something that has been very successfully modeled using fluid dynamics. So fluid dynamics is the ideal transport approach to model these types of phenomena. And it's, generally speaking, it's called elliptic collective flow. This particular type of flow, which comes out of this almond shape initial condition, is called elliptic flow. And there was a seminal paper by Luzum and Romachka back in 2008, where they showed that the anisotropy in the emission, yes, as a function of impact parameter, which is this x-axis here, yes, is very sensitive to the amount of shear viscosity or specific shear viscosity that you put into your fluid dynamical calculation. So this is very early data, and it's a very rudimentary fluid dynamical calculation, but it shows the sensitivity, and that meant that this observable has become one of the key tools that we need if we want to make any statements about the viscosities of the system. And this is something, this property, this elliptic flow is not something that is only observed in heavy ion collisions. Here you have a cloud of lithium atoms, ultra-cold lithium atoms released from a magneto-optical trap. And these lithium atoms are in a magnetic field that is dialed to a Feshbach resonance that makes them maximally strongly interacting. And what you can see is exactly this elliptic flow phenomenon where the system expands mostly along its short axis. Yes, so these were experiments done in 2002 at Duke University, and it shows that elliptic flow is a general feature of strongly interacting systems. Okay, so here is essentially the data that goes in. I'm not going to discuss this in great detail. It's the mean transverse momenta of a number of different particle species measured. It is the elliptic flow coefficients that characterize this elliptic flow that we talked about, and it is particle multiplicities. And the key feature we are on the lookout for is we want to have data with small error bars. So with small uncertainties. And those classes of data give us these small uncertainties. Okay, so now let's come to the mathematical part of the analysis. Yes, and there, the most interesting thing are these Gaussian process emulators. So I have a model. This model has about 15 parameters. And I want to learn what is the response of my model towards variation of these parameters. All right. So I could do a brute force analysis. Yes, I say I have 14 model parameters. I will select 9 different values of impact parameter which sort of characterizes the shape of my element. Yes, and I will evaluate my model for 20 different values for each parameter so that I get a good feeling of how my model responds to a change in the parameter values. So this means that I need to evaluate my model at 9 times 20 to the 14 points in parameter space. Now, just calculating one heavy ion collision, evaluating my model once is not good enough since there are probabilistic parts in my calculation, and so I need to average over multiple instances of that simulation. Yes, on average, I need about 10 to the 4 events per point. Yes, so this means that in order to investigate my parameter space, I need to calculate 10 to the 18 collision events. Each of these collision events takes about 1 hour on CPU. So I need 10 to the 18 hours of CPU time. This is 2 billion years of 100% use of the Titan supercomputer at Oak Ridge National Lab, which is a massively parallel Cray computer. And then you start running a Markov chain Monte Carlo to actually find out which of these points in my parameter space optimally describes the data. So clearly this is not feasible. And for the longest time, when we were toying around with doing this type of analysis, this was the end point. No way to do this, give up, move on. All right, so we need to find techniques that cut down the CPU needed by at least 10 orders of magnitude. And it turns out that our friends in the statistical sciences have exactly this tool, and it's called the Gaussian process emulator. So a Gaussian process is just a stochastic function that maps inputs to normally distributed outputs, and they're specified by a mean and a covariance function. So it's basically a somewhat cleverer way of interpolating between points at which you know the outcome of your calculation. And these Gaussian process emulators are popular in machine learning. And so what you can do is you can train these Gaussian process emulators on a set of calculations that you perform. Those are the black points here in this little cartoon. And then the Gaussian process emulators will give you values, predictions for all the points in between. And these predictions will have some uncertainty associated with them, which grows the farther away you go from the points at which your process emulators actually have been calibrated or have learned on. Yes, and that is very nice because it encapsulates the uncertainty in your interpolation as you go far away from the points at which you've really evaluated your physics model. And the other advantage of these Gaussian process emulators is that once you have trained them, which takes perhaps a couple of days, they give you a result very, very fast. So instead of waiting, multiple hours, 10 to the 4 hours for a full model calculation at one point in parameter space to complete, that's perhaps a few microseconds or so, and boom, the Gaussian process emulator tells you what the outcome is in terms of the observables, right? So that's absolutely crucial. Now the other thing is that you don't need that many points in parameter space to train your Gaussian process emulators. As a matter of fact, if you have an n-dimensional parameter space, you can get away with as little as 10n points, yes, to train these emulators. So instead of running my physics model on this huge grid of points, yes, for a 15-dimensional parameter space, I can get away with just evaluating my point at 150 points in parameter space. 150 compared to, what was it, 10 to the power of 18? That's huge, right? Now, the only thing I need to make sure of is when I train my Gaussian process emulators that I have, a good sample of points that cover my entire parameter space. And one way to generate such a sparse distribution of points that evenly fills my parameter space is an algorithm called the Maximin Latin hypercube. And then so we use that algorithm to generate points at which we evaluate our physics model, where we really run the hydro. And then the outcome of those hydro simulations is then being used to train the Gaussian process emulators so that we can then, access these emulators to get at the values for any point in between. Yes. So this, in our case, we had 15 model parameters. We did 9 centrality bins, 2 beam energies. We ended up with a Latin hypercube that had about 500 points, which meant that we calculated about 35 million events. So that's 35 times 10 to the 6 versus, what was it, above 10 to the 18, doesn't matter, right? We shaved off more than 10 orders of magnitude in CPU time. Yes, that's what matters. All right, well, 35 million events, yes, 35 million CPU hours is still nothing to sneer at. It takes a lot of time. As a matter of fact, we managed to shave it down a little bit more and went to NERSC, yes, which has another Cray supercomputer, massively parallel, yes, 2.5 petaflops, and we developed a workflow that allowed us to run our jobs on 1,000 nodes per job, so which meant we were running on 48,000 cores simultaneously. And our entire model design with 30 million events, we were able to push through NERSC in one day. 2 billion years versus one day. And we probably weren't even using the entire machine to ourselves. Yes, and as a matter of fact, we were not. There were other groups working on that machine. Well, okay, here in that snapshot, actually, we were the only ones in Edison, but I assure you there were other users as well, perhaps not with those massive jobs. Yeah. Okay, so this is how we were able to reduce the computational expense to a point where we could do the analysis. All of this is rooted on Bayes' theorem, which basically says that an object called the posterior distribution is proportional to a likelihood function times a prior. Yes. So what are these things? Yes. The posterior distribution is essentially the probability distribution for all of your parameters that you are calibrating, for all the parameters that you want to optimize. Yes, the likelihood function is something like a measure of how far away is your calculation from describing the experimental data. So what is the distance between the data that you evaluate at your point, at the point in parameter space at which you are sitting, and the data that is measured? Yes, how far away are you between, what's the distance, figuratively speaking, or the norm that separates model output from experimental output? And the prior is, any kind of information that you can stick in to make your analysis easier. Yes. So for example, one thing that could be a prior is if I know that the bulk viscosity is always peaked at TC. Yes. Then I could reduce my parameters by 1 if I say, okay, the peak temperature for my bulk viscosity is TC, and I could simplify the function, right? So that would be some kind of prior that I put in. Or I could argue that, say, the transition temperature between my hydro calculation and the Boltzmann equation evolution, has to fall in a certain range. Yes, so that is a prior. Yes, if I can, pinpoint that range fairly precisely, then I can put that in as a prior, and I don't need to explore such a big chunk of my parameter space. So priors are important, and they inform the outcome of the analysis as much as the likelihood function. And then in the end, what you do is a Markov chain Monte Carlo random walk through parameter space. Physicists also know this as Metropolis-Hastings kind of algorithm. Basically, in this random walk, you move from one point in parameter space to the next, and if you get better, closer to the data, then you always move in that direction. And if not, then still then you still have a limited probability to executing that step, which allows you to not get caught in false minima. Yes, and if once you have done enough steps, you have sort of converged to the best possible point in parameter space. Okay, so colloquially, we also refer to the prior as all the model calculations that are being done over the full range of our parameter space before we do the Bayesian analysis. That is what you see here. These are not bands, these are individual lines, 500 individual lines per color, per plot, yes, for running our physics model at each point, at each of our 500 points in parameter space, and comparing the outcome of that to the experimental data, which are the black symbols. And you can see that, yes, our parameter space broadly covers the experimental data, but it would be awfully hard, just by eye to figure out, which of these lines would be the best. Yes. So after you do your Bayesian analysis and your Markov chain Monte Carlo, it reduces to this very, very good agreement between model and data. Yes, and again, these are not curves. These are, again, my 500 lines. But now what I've done is I've sampled 500 values from the posterior distribution that comes out of my Bayesian analysis. So I've taken the probability distributions for all my parameters. I've sampled these 500 times and run them through my Gaussian process emulators to get these curves. Okay, so you can see that this optimization technique worked very, very well. All right, what do we learn? So the main outcome of this analysis really is what's called the posterior distribution, which in its diagonals encodes the probability distribution of each parameter, integrating out all others. And in the off diagonals, you get pairwise distributions that show dependencies, correlations between parameters. So this is the posterior distribution that we get out for all of our parameters. And there is a huge amount of information in there, which I can't even possibly start telling you all about. Yes. So so a couple of global features. What you want to see are these nicely peaked structures here. Yes, a nice sharp peak means that the analysis was able to determine your parameter with a small uncertainty. All right, on the other hand, if you get something that is fairly broad, yes, this means that the analysis was not really sensitive at all to any value of the parameter that you deemed reasonable. Yes, and that tells you that either you don't have the right data to compare to, or that your model parameter really isn't that meaningful. And that's also a very, very interesting piece of knowledge to have. Yes, and sometimes you end up with your peak being sort of towards the edge, and that could be indicative of your prior range for your parameter to be too constrained. Or if there are really physics issues with it, then it tells you that your analysis really is sort of heading towards an edge here. Okay, so you can see that mostly, but not always, we get these nice peaks, and we learn a lot from these. So for one, the switching temperature between our hydro and our Boltzmann is very well constrained, so that's good. And it is at a value of 152 MeV in temperature, which is also very good, given that the transition temperature from Quark-Gluon Plasma to hadrons is a few MeV above that. So we get out a reasonable result. Yes, but it also shows us that once the system has converted into hadrons, fluid dynamics very quickly is not the best description anymore, and you should switch to a microscopic approach. All right, then we have here something that I'm not going to talk about in detail for the colloquium, but for the few experts in the audience, we have very clear indications from our initial condition model that one particular type of theory, which is based on a saturation picture, yes, is the right theory for describing the initial state of a heavy ion collision. Yes, and that's a theory called IP plasma or EKRT. Yeah, so two manifestations of the same thing, roughly. And we get very, very tight constraints on that. Yes, something I'm going to talk about a little bit more are the three parameters that govern the temperature dependence of the specific shear viscosity. Yes, and you see here that there is a nice uncertainty band that we get out. By the way, here the line, here is the 1/4 pi line, that is the conjecture from string theory. Yes, and really towards TC, we almost hit that. Now there's no reason why we should hit it, but it's fascinating that QCD as a system really gets very, very close to that conjectured bound. And then for the bulk viscosity, what you see are very, very large uncertainty bands. So clearly we haven't quite figured out yet how to make a good statement on the specific bulk viscosity. We can say that the system definitely prefers having a bulk viscosity, but we can't really say much about the shape or position of the peak. All right, and also what you see is that my uncertainty band sort of broadens as I go higher in temperature. And that's an interesting feature. It's also well understood. Our system lives longer at lower temperatures, yes, than at the high temperatures that got only excited, so to speak, or formed at the very beginning of the collision. And thus there is more response time for the system to build up flows in a temperature range between 200 or 150 and 250 MeV, and that's where our uncertainty bands are the smallest. Yes, and the higher you go, the bigger our uncertainty bands go. Yes, I would say one more thing. As one of our priors, we have restricted the slope of our specific shear viscosity to be either horizontal or positive. Yes, we have excluded negative slopes for the very reason that you can do perturbative QCD calculations of the temperature dependence of eta over S in the hot thermal loop limit. And those calculations show a logarithmic rise of eta over S with temperature, so definitely a positive slope. And so we felt that a negative slope would be not physical, and that's excluded in our prior. I know of a subsequent analysis by another group that did not make this assumption, And this resulted in their uncertainty bands up here being quite a bit larger. Yes. This, I would argue, is one case where putting a prior in is actually advantageous, since physics clearly argues for the slope being either positive or at most 0. And where not putting a prior in can actually affect the meaningful or the usefulness of your outcome, because your uncertainty bands just get bigger, and that means that you don't learn so much. All right. How am I doing with time? Should I come to the conclusion, or do I still have a little bit more time left?
Well, it's up to you, really. We could spare some time if you need something to say.
Okay, I'm just going to flash those few slides. I'm not going to describe them in detail, but I want to give you the buzzwords. Yes. So this analysis is complicated, right? You know, I've rolled out a very complex machinery, from a fairly complex computational model to a lot of mathematical machinery. You know, my Gaussian process emulators, my Markov chain Monte Carlo, all of that. So you may wonder, you know, how much of this is really precision science, and how much is sort of uncontrolled approximations and smoke and mirrors, so to speak. Yes. So how much can you trust what I showed you? So first one thing you have to do, of course, is for your Gaussian process emulators is you have to validate them. You have to test that they actually give something reasonable. And the way to do that is that you train your Gaussian process emulators on a subset of your data, and then you use them to predict the other subset of the data that you have. Data, I mean calculations. And if your Gaussian process emulators perform 100% accurate, then they would be all on the diagonal of observed versus predicted. You can see there's a little bit of noise there, and that's okay, since there is uncertainty baked into these Gaussian process emulators. So that validation was successful. You know, then you should do a verification. So what we got out were these posterior distributions, and we can now you know, read out of the posterior distributions, read off the parameter values at the maximum posterior probability, and use these parameter values to do a model calculation. Yes, so we don't use our Gaussian process emulators to look at the data. We use our physics model really to calculate a set of events and compare that to the data. That's what's done here, and that works again very well. Then we could do predictions. We could now use our model with the parameters that we have extracted, and we could calculate observables that were not part of our calibration, not part of our fit, and see whether our model actually is able to describe those measurements. So that's what we have done here with certain correlations of event-by-event fluctuations of flow harmonics. These require an insane amount of events. So our uncertainty bands are somewhat large, given that we didn't have quite enough events available to do that, but it works reasonably well nevertheless, right? So our model has predictive power. We can predict other observables that we haven't calibrated against. Yes, and last but not least, there is something which is called a closure test. So we need to verify that our analysis can recover true values of the parameters. So the way to do that is that you take your model and you generate fake data. So you put in a certain value for your specific shear viscosity, for your bulk viscosity, for your initial conditions. Yes, you run your model and you do the same data reduction you would do with the experiment, meaning you calculate the observables and you generate the histograms just like you would do with the experiment. And then you use those data points as experimental data and run your analysis on them and see whether your analysis can extract that shear viscosity that was actually used in order to generate those data points. Yes, and you should not expect perfect agreement, since for one, there are uncertainties involved, and for two, there is also a lot of data reduction that takes place when you take the information content that the model provides, you know, the full final state of all the particles, and reduce that to a set of histograms that have been measured by, that look like the ones measured by the experiment. Yes, so this information reduction will give you an added measure of uncertainty. So you need to take the the uncertainty band seriously, but what you can see here is between the analysis of the fake data and the actual real value of the viscosities that were put in, we certainly are well within the uncertainty bands and we're able pretty well to recover those physics features. Yes, so closure test is very, very important to make sure that whatever you assume your model to do, right, that it recovers that physics. Okay, so I'm going to summarize. We have created a comprehensive set of computational models to describe the dynamical evolution of ultrarelativistic heavy-ion collisions. This was this combination of fluid dynamics plus Boltzmann transport. We have developed a framework utilizing Bayesian statistics and high-performance computing to execute a model-to-data calibration with uncertainty quantification. And we've been able to apply this framework and our model for the first quantitative determination of the temperature dependence of the QGP specific shear viscosity. And it turns out, if you compare our band here with the ones for water and helium and nitrogen, that this is really the lowest specific shear viscosity of any known substance in nature by far. Yes, the only other thing that can come close are our ultra-cold lithium gases, but even they have Eta/S values that are more somewhere up here. All right, where do we go from here? We can put in more experimental data in our analysis, which will ultimately allow us to also study the chemical potential dependence of the transport coefficients. We can look at asymmetric collision systems. We can look at other experimental data, jets and hard probes. I mean, jets and heavy quarks, for example, for the determination of the heavy flavor transport coefficient. And also this analysis doesn't really care whether you use a hydro with a Boltzmann transport. If you prefer, some kind of strong coupling calculation or, a Vlasov-Wheeling-Uhlenbeck calculation or a microscopic kinetic theory, yes, as long as you have well-defined parameters that you can vary, yes, you can use that instead, right? And use our framework to calibrate your model to the experimental data and see what comes out. Yes, so this work was sponsored by DOE, NSF. CPU time was provided by NERSC and the Open Science Grid. And I need to give, of course, a lot of credit to historical efforts that preceded this analysis. That was the MADI collaboration led by Scott Pratt at MSU from 2009 to 2014. And I mean, Scott has been talking about doing this kind of stuff already in 2000. Yes, that slide with all the arrows between the parameters and the observables, I lifted from a presentation that Scott gave way back then. So this is something that we've been trying to do for a long time. And it has taken a lot of people, both on the theory side, on the math side, on the experimental side, to make this possible, right? So this is not something that you do in a year. It's a community effort. Yes, I want to give credit to the postdocs and grad students at Duke who have pushed this forward, in particular, Jonah and Scott. Jonah leads now a data science group at Lowe's. Scott does data science at IQVIA. Guayao and Mingru were doing this in the heavy quark sector. Guayao is at LBNL. Mingru is a data scientist at Capital One. And Jean-François is a research scientist at Duke right now. My stats colleagues were Robert Wolpert, faculty member in the statistical sciences, and Snehalata Husu-Bazar, who was at the University of Wyoming, with their grad students, Jay Coleman and Peter Marcy. And I have to give a lot of credit to my hydro colleagues at Ohio State, Ulrich Heinz, Jie Liu, and Chun Shen, who basically developed the hydrodynamic model that we were using. Every piece of code that we have used for analysis is available online, open source. So I invite you to download the codes, to play around with them, to see for yourself how we have done it, and to use that for your own purposes and analysis. All right, thank you very much. I think I'm done.
Okay, thank you very much for a nice presentation. We have a number of questions in line, so I'll start with the first question, which was written in the chat message because the person cannot ask himself. So it's coming from Krishna Ariel. He says, how you minimize randomization effect in your calculation?
Not quite sure about this question, but essentially, you know, there is of course statistical fluctuations in there, you know, and then that's due to the nature of the measurement. And now for the experiments, it's easy because they measure millions and millions of events, right? And that's what gets the statistical error bars to be so small. And on the theory side, we use about 10 to the 4 events to get our statistical error bars small. Theory events are better than experimental events, you know, due to the limited acceptance that the experiment has and the 4 pi acceptance that the theory has. But we have to account for, you know, a lot of uncertainties, right? So our theory comes with an uncertainty allocation, yes? So we are assuming that our theory, as it describes these different spectra and distributions, is not better than, you know, has, you know, 5 or 10% deviation.
Right.
Yes. So that's something that's part of the Bayesian analysis. So if you look, hold on, I should go back. I glossed over this a little bit. Wait. I'm not sure why my keynote is.
Well, it did its job.
Okay.
Yeah.
So let me see if I go back to where do I have Bayes' theorem? Zup. Here. Yes. So part of the likelihood function is a covariance matrix that contains both experimental and model uncertainties, both correlated and uncorrelated. Yes. And so the model uncertainty we estimate as being 5%.
Okay. I think it's a sort of really loaded question. So let's move to the next one. So the next is Farid Tagavi. You can ask yourself. Go ahead.
Hello, thank you for your nice talk. So I have a question. You had you used several experimental measurements as input to fix the 3 parameters of the model. Specifically, you use the flow harmonics, the elliptic flow fluctuations, and then after as the output, you test the output of your model with symmetric cumulant measurements.
Yes.
Actually, I would like to ask about this point. I'm not sure this is a correct statement. If we say the symmetric cumulants are more sensitive to shear viscosity over entropy compared to flow harmonics. What happens if we use symmetric cumulants as input and then check the?
That's a good question. In principle, it can be done. In practice, these cumulants just require a lot more events to do, right? And so probably a factor of 100 more events I need in order to calculate these cumulants.
Yeah.
And that would mean that I go from 3 million CPU hours to 300 million CPU hours if I wanted to do this analysis based on a symmetric cumulants. And that's just right now, that's probably a step too far in terms of how much CPU time I can get. Yes, our annual allocation at NERSC is between 5 million and 10 million hours per year. And I'm trying to get about 2 to 3 such analysis done per year. And that sort of constrains us in terms of what kind of data we can use in order to make this analysis. As you will see, for example, the other thing that we haven't used is, and then I get asked about this almost every time, why didn't I use the PT dependence of the V2 coefficients?
Okay.
And that's the same story, right? If you go up to reasonable values in PT, you need a lot more events to get these than the number of events that I've used.
Okay, I think we can go to the next question. Andrei Sternetz, go ahead.
Yes, thank you. Thank you very much for a very nice talk. I wonder if you could elaborate a little bit on the slide where you had this temperature dependence of the shear viscosity and bulk viscosity. And you mentioned that the assumption was, yes, exactly. The assumption, there was a prior assumption, right, about the positive slope of this dependence. And then there is some other group which did not have this assumption. I'm curious if then you would have a function which is not monotonic, or it was still monotonic, but just with a larger uncertainty. Because in general, I mean, just to put this in perspective, in principle, there is no theorem, right? Even in the string theory results and so on, that would tell you that there is an absolute minimum, right? It's a speculation based on a result for infinitely strongly coupled specific class of quantum field theories. And then in principle, it is conceivable that this dependence has a minimum somewhere. So it goes, so it's not monotonic. And in fact, I don't know if in normal substances, and I would really love somebody to enlighten me on this, if in normal substances in a given phase, the dependence of transport coefficients is monotonic or not. Do we have examples where it's not monotonic? Right, so could you just elaborate on this?
So this analysis that I referred to is an analysis that is yet to be published. It's going to hit the preprint server in a few weeks, and then I can, then I could point you towards.
Okay.
But what you would see is that it still would be monotonic. Yes, just your uncertainty bands would sort of. So this uncertainty band would curve down more in this direction. Yes, and the uncertainty band actually curves up somewhat more, I believe. Yes, but mostly I think it's the shape of the uncertainty bands bulges more towards in this temperature range here.
Okay. All right. Yeah. Thank you.
Okay. Next question from Lipei Du.
Thank you. So, I mean, when you take some extreme values for some of the parameters, your part of the model might be broken already. So I wonder whether you took special care of these cases when you get the distribution functions for it.
Okay, so we took special care in a sense that we have our priors. Yes, we used, but what we used in this analysis was so-called flat priors. So this means that we allow parameters to have a non-zero value within a certain range, and these parameters are zero outside of that range. Yes, and the ranges that we picked for our parameters are ranges that I would not call that extreme, or at least these are ranges that would allow for our physics model to still be applicable. Yes, so we are not pushing the physics model beyond its reasonable limits. And that is by the way we bound the parameter ranges that we explore. Does that make sense?
Yes, but do you think some like combinations, some edge values might result in broken simulation?
I wouldn't call it broken, but the outcome clearly is something that, is not in any way or form justified by nature. Yes. So,
okay.
So when you say broken, for me, broken is if I run my hydro beyond its limits of applicability, meaning that either the viscosities get too large, or the initial condition, the initial state is too far out of whack, out of equilibrium. Yeah, and that's something that we've been trying to avoid. Yes. Now this is something that other people in this field have investigated. One way you investigate that is by evaluating the Knudsen number for the hydro. And most of these Knudsen number analysis have shown that for nucleus-nucleus collisions, lead-lead collisions, like I showed you here, we are well in the range of applicability for hydro. Where this gets questionable is if you go into small systems, proto-nucleus, where there are a number of cases where this is pushing the envelope.
Okay, thank you.
Okay, the next question is again, but for Rita Gabi. Go ahead.
I'm not sure, probably you answered my question. So I just want to ask about the shear viscosity over entropy on a small system. Is it possible to measure?
Yes, so there are groups, of course, who are much more prominent in doing this than our group. Yes, Colorado, for example, Romachka and company have put a lot of thought into this for small systems. We have done an analysis, a joint analysis of lead-lead and proto-nucleus. And the problem that we faced was, again, due to lack of CPU time, when we went to PA, we only looked at one collisional energy. Yes, and so you see here, and I'm sorry, I lost my pointer. What you see here in that eta over S plot is a function of temperature. The blue band is the band that I talked about, which is the analysis of just lead-lead for two collisional energies. The orange band is an analysis that only had one collisional energy, but lead-lead and proton-lead. And clearly, playing one against the other was a bad idea. Yes, the uncertainty band is a lot bigger if we just do one collisional energy than if we do two collisional energies. And that has to do with the fact that you are getting less resolution in how you probe temperature dependence of different quantities if you don't have two beam energies that give you different starting temperatures. Right? So we should have included two collision energies in that analysis, and that would have shrunk our uncertainty bands, but we did not do that since the joint lead-lead and proton-lead analysis necessitated a bigger CPU expenditure since you have to go from 2D hydro at mid-rapidity, you have to do something which is more geared towards 3D, and it gets difficult. So this is work in progress.
Okay, the next question from Keiju.
Hello, Steffen. Here's Kai. So I want to ask, so suppose there might exist some event-by-event fluctuation informations, but not contained in the event averaged observables. And let's suppose this are also related to some unknown but important physics. So how the procedure here can possibly capture this information?
So the procedure, the Bayesian analysis would be perfectly okay with that. Yes. So as long as your physics model captures the physics that you're talking about, then you're fine. Yes. Since at the end, my Gaussian process emulators are trained on the experimental observables. Yes, so if you have fluctuation observables, you would train them on the fluctuation observables. But of course, in order to train them, you need a physics model that does the fluctuation observables right.
I mean, you're not using the high dimensional rod data, but using some averaged observables like the PT spectra or V2, V3, not the PT5 spectra.
Yes, but even if but on the experimental side, you would also come up with some kind of fluctuation measures, some kind of D measure or what have you. Yes. So you're constructing fluctuation observables on the experimental side, and I can calibrate on those. Yes, I'm never going to calibrate on the individual final state particles, but I'm going to calibrate on whatever fluctuation measure you come up with.
Okay.
Okay, I have another question. It's actually, I have my own question. It's related to the sensitivity of this extracted data for shear viscosity to V3 and V4, observable V3 and V4. Are they really affecting the information about extracted shear viscosity, or are they just mostly irrelevant?
Okay. Hold on. Yes. So, hold on. No, wrong figure.
So, sort of how important they were for this
so for the, I would say the V3 is very important. So as you can see, we calibrated on V2, V3, and V4. Yes, we know that V3 is very important in order to get our initial state parameters, our Trento parameters right. Yes, and I guess V4 goes in a similar direction. Yes, so that's where they play a major role. And of course, there is some interplay between V2 and V3. So I wouldn't want to cut them out.
So maybe to rephrase it, if you didn't have that information about V3, V4 from the data, would your shear viscosity be very different as a result, extracted from the data, or the errors will be much bigger?
I would say the errors would be bigger, and I would lose any way of constraining my initial state.
I see.
Yes, bear in mind that the outcome of this analysis is not only the shear viscosity, but also everything that characterizes the initial state.
Right. Right. Well, the general sort of idea behind the question is that with the shear viscosity, the higher are the moments, then essentially the less and less visible they will be. Essentially, they will be washed away, and therefore, in reverse, they shouldn't be that important as V2, for example, in extracting the actual value.
Now, what we can always do, yes, and we have not done this, but it's easy. Easy means it only takes us about 2 days of CPU time. On a single processor, right? Not on RHIC. Yes, we can always rerun our analysis and take that data out. Yes, so that would be perfectly fine.
Well, also the origin of those might be very different than the origin of V2.
Yes. Yeah. All right. I'm very sorry, but I hear at my door that my next appointment is waiting for me.
Right. I think we exhausted the questions anyway. So I would like to thank you once again for a nice presentation and for taking all this time to answer the questions.
Sure. Thank you, Igor. I really appreciate the opportunity to be talking to you all.
Okay.
And if there are more questions, anybody in the audience, please feel free to email me. Yes, and I'll be happy to answer.
Okay.